Hello Math30-2 and welcome to Mutually Exclusive Events, the probability of mutually exclusive events. So today we're going to be looking at and and or again. Remember from the unit before when we did and or? Well, it's coming back. So remember, the union sign means or, the intersection sign means and. So when we're talking about probability, this is going to say A or B. This is A and B. Okay? So A union B is or A or B. A intersect B is A and B. So here we go. Let's go to this first little exploratory here. So it says investigating mutually exclusive events. So consider an experiment of rolling a die. You roll a die, there's numbers 1 to 6. Now it says event A is all even numbers. So what are my even numbers? 2, 4, and 6. Event B says all odd numbers. What are my odd numbers? 1, 3, and 5. So, there we're done part A. Part B says list the outcomes for event A. Okay, so event A, what are my outcomes? I can have 2, 4, or I may have 6. Those are all of the even rolls I may have. Then it says event B. Okay, list the outcomes for event B. So I can have 1, 3, or 5. Pretty simple. Now, what is the intersect? List the intersect. Well, you can't have a number that's odd and even at the same time. So when we roll a die, we can't have an odd or even number. So then, this is actually an empty set. Remember that notation? It's an empty set. Okay, so, oh, sorry, it says A or B. Whoops, A or B. So let's look at event A or B. Well, everything is either even or odd. So A or B is, we have 2, 4, 6, 1, 3, and 5. So it's all of them. 1, 2, 3. So that's all, because A union B is or. So now we're going to look at the intersection, A and B. So, like I said before, if it's odd, it can't be even. If it's even, it can't be odd. And we look, there's no overlap in the circles. Therefore, it's an empty set. Now, let's look at number C. C is stating, let n represent the number of the probability outcomes, so the number of outcomes. So how many are there in A? So how many total outcomes can we have in A? We could have 2, 4, or 6. So we have 3 different ones, right? In B, we have 1, 2, 3. Outcomes. Now, A or B, how many do we have? 1, 2, 3, 4, 5, 6. That's all the outcomes. A and B? Well, there's none. Okay? So determine the following probability. So what is the probability of rolling event A? So getting an even. What is the probability? Well, half of your things are even. So that is 3 out of 6. Which is actually equal to 1 out of 2. What's the probability of rolling a B? And that's all the other ones. That's all the odds. So that's 3 out of 6, which is 1 out of 2. So now it says, what is the probability of rolling an A or B? Well, how many? That's all of them. It's everything. They're either odd or even. There's no exemptions. So that's 6 out of 6, which is equal to 1. That's 100%. What is the probability of rolling an odd and an even? That's what this is saying. Odd and an even. Well, unless if we're rolling twice, that's impossible. So it's 0 for 6, which is 0%. There's absolutely no way we could roll odd and an even on one die. So these here are considered mutually exclusive. Why are they mutually exclusive? Because there's no overlap. Okay? Here's a little thing that we're going to verify at the very bottom here about mutually exclusive. It says, verify the following, that if we have odd or even, it is equal to, the number of odd or evens is equal to the number of odd plus the number of even. Well, let's see. How many odd or evens are there? There are 6 odd or evens, right? Now, number of odd, in this case, number of event A, there are 3. Number of event B plus 3 equals 6. Hey, in our scenario, that's true. Therefore, they must be mutually exclusive. It's kind of a definition of it. So let's take a look at the second part here. It says the probability of being odd or even is the same as the probability of odd plus the probability of being even. Okay, probability is 1, right? What's the probability of being odd? Well, that's 1/2. We found that out up here. What's the probability of being even? Well, that's found out right there. Well, 1/2 plus 1/2 is equal to 2/2, which is equal to 1. 1. Hey, look at that. Works out. So then this one is as well mutually exclusive. Okay. So now we're looking at a new situation, non-mutually exclusive is getting into. Look at these circles. There's an overlap. Key thing there. There's an overlap in those circles. So consider rolling a die. Now A is even. That's a game. So I'm just going to write them out here. So even is 2, 4, and 6. That is A. I'm going to write it here. 2, 4, and 6. All of those are invented here. I'm kind of doing B first. It just makes more sense to do B first. So it's 2, 4, and 6. Now, and B is multiples of 3. So which ones are multiples of 3? Well, I have 3 and 6. That's it. Well, what is the total amount of numbers we could have? I could also have a 1. I could have a, well, 2 is used, 3, and a 5. 1 and 5 are also not used, aren't they? Because my whole sample space is 1 to 6. 1, 2, 3, 4, 5, 6. That's my sample. This is my sample space, right? And they're not all being used. What's being used? 1's not being used, and 5's not being used. That's interesting. So now, let's put them all in the Venn diagram. So we have, first let's put in, we always put in our centers, what's being shared. Our 6's are being shared. So 6 goes in the middle. What else is in A? 2 and 4. 2, 4. Let's look at B. There's 3. And what isn't in any of them? 1 and 5. So I can put 1 there and a 5 there. They are not inside our circle. They are not part of our sample space that we want. Okay. Now, what is the probability? Or sorry, not the probability. So what are A or B? Let's look at all the A's or B's. So that's 2, 4, 6, and 3. So that is 2, 3, 4, and 6. Remember, it's everything in both, A or B. Now, the event A and B, this is back from our first unit. That's just the intersection. That's 6, okay? That's element 6. Now, complete the following. So what is the number in A? Well, we have 1, 2, 3. There are 3 elements in A. 3 outcomes in A, in this case. What about the number of outcomes in B? So the number that can, how many of them can be multiples of 3? We have 1, 2. There's 2 in there. Now it says, how many could be even or multiples of 3? Well, let's count this up. 1, 2, 3, 4. There's 4 in my union. Now, how many is in A and B? Well, that's only 6 could be a multiple of 3 or even. So there's only 1 of them in there. Okay. So now it says determine the following probabilities. Okay. So, probability of A. Well, we have 1, 2, 3. Oh, so that's 3 out of 6. There's a total of 6 in my sample space, which is the same as 1 over 2. What's the probability of B? Okay, B, there's 2. Well, that's 2 out of 6, which is the same as, we cancel it down, we're going to get 1 out of 3. Now, what is the probability of A or B? A or B. That's 1, 2, 3, 4. There's 4 in the union of A or B, so that's 4 out of 6, which is the same as 2 over 3. Then it says A and B. Well, that's only the 6. Only 6 could be even and a multiple of 3 when rolling a die. So we end up getting 1 out of 6. Okay, now, if we notice, there's an overlap here. And because of this overlap, these are mutually exclusive, these are not mutually exclusive events, okay? These are not mutually exclusive. There's an overlap. So these tend to be the formulas for the mutually exclusive events down here. So let's see if it's true. So it says the number of events or the number of outcomes that are A or B. Well, I have 4 of them, right? That was done up here, right? 4. So we have 4. Okay? Next it says is equal to the number of A events. Well, the number of A events is done up here, which is 3. So we're going to have 3. Plus the number of B events. B, 2. 2, right? Because that's the number of odd numbers, or multiples of 3. Now minus the intersection, the middle, which is right there. Well, that and is the intersection, which is 1. Well, we add this up, that's 5 minus 1 is 4. Hey, look, that works beautifully. Nice. Now we take a look at number 2. Well, we want P or B. So the probability is 4 over 6. I'm going to leave it as the big ones because for addition purposes. Or actually I'm going to put the simplified one. 2 out of 3. Okay? So we could practice adding fractions. So now we're going to go probability of A. That's 1 over 2. Probability of B is 1 over 3. We just did that over, it's right there. Probability of, and then we're subtracting now the probability of A and B, which is 1 over 6. Now, do remember, to add fractions, what do we need? Common denominators. Without common denominators, we cannot add. So, 1 over 2, common denominator between all 3 of these is going to be 6. So I have to multiply these by 2, multiply by 2, or multiply, sorry, by 3, so I'm going to get 3 over 6. That's the same as a 1/2. Plus, this by 2, and I'm going to get 2 over 6, minus 1 over 6. What do we end up getting? Add those together, that's 4 over 6, minus, that's 5 out of 6, minus 1 out of 6 is 4 out of 6. Now, is 2 out of 3 the same as 4 over 6? Yes, it is. Look at that. Look how that works. So, mutually exclusive events, your intersection must be equal 0. So, for it to be mutually exclusive, there can't be anything in there. Your number of mutual events, or your number of intersection, your number of events that are event A and event B must be equal to 0. There can't be any overlap, okay? And the reason why we have to subtract for the non-mutually exclusive is because if we don't subtract this overlap, it's counted twice. And we don't want to count something twice in the probability, because then our probability will, in the end, end up over 100. We can't count something that's counted in probability for 2 different things, okay? So, here we go. These are the formulas that you have to know. They're going to be on your formula sheets. So let's try class example number 1. A die is rolled. Okay? Zoom in a bit. Okay, a die is rolled. Okay? Event A. Even number occurs. Okay, well, okay, and event B. We're just saying if they're mutually exclusive. Odd numbers occur. So, if I did this right here, event A and event B, even and odd, they cannot intersect. All my odds and all my evens are there. So let's even try it out here. All my odds, all my evens are 2, 4, 6. All of my odds are 1, 3, 5. This is a die, right? 1 to 6. None of them overlap. This is mutually exclusive. I'm just going to put ME for mutually exclusive. Okay. Let's take a look at the next one. So we're looking at standard deck of cards. Event A, a face card is selected. We could have king, queen, king, or jack. Event B, a club is selected. Well, wait a minute. Can't there be a king of clubs, and a queen of clubs, and a jack of clubs? Well, yeah. So there is an overlap there. If we did this, there would be an overlap. We have a queen, a king, and a jack of clubs all in that middle. Right? They're in both. So, what does that mean? This is not mutually exclusive. Or I'll put this in a line through it. It's not mutually exclusive. Ooh, got a little bit too carried away. There. So, now let's take a look at the next experiment. 2 dice are thrown. The dice both show the same. So if we show 2 dice, we're throwing 2 dice. The dice both show the same value. Okay? So some examples are 1 and 1, 2 and 2, 3 and 3, 4 and 4, and then 5 and 5, 6 and 6. And then the total score is 11. Well, if we get 11, is there any pair that can make 11? Well, if it's a pair of the same numbers, it must be even. So there isn't going to be an overlap here. There are none that will overlap. So this is mutually exclusive. Okay? So, there we go. Now, complementary events are, notice that mutually exclusive event A, even number occurs and odd number occurs, right? So if you look at A, you can only have even or odd. Those are complementary events, meaning if we're looking at even, the complementary events of the even are the odd, and that will make up your full amount of outcomes. Your complementary event means if you have 2 events and they make up the full amount of outcomes, they're complementary. So, here we go. Take a look at this one here now. Example 2. Consider the experiment of drawing a card from a standard deck of cards. The following events are defined. So, a face card is selected. So we want to just look at which of these are mutually exclusive. So face card is selected. Alright. Now, if a face card is selected, can it be a red card? Yes. These are not mutually exclusive. Can it be a club card? Yeah. Oh, it's not mutually exclusive. Can it be an ace? No, no face cards are aces. So I know A and D are mutually exclusive. Excellent. Okay, let's look at the next one. Can a face card be a black card? Well, yeah, a face card could be a black card. Next one, red card is selected. Can a red card be a club? No. So, B and C. Those are mutually exclusive. Okay, red card selected. Can a red card be an ace? Yes. Now, can a red card be a black card? That's true too. So, red card can be a black card. So, that is B and E. Okay, so we have then black. Now, we're done that. So let's look at the club. Club can be an ace, club is black. Ace can be black. There, we're done. Now, the next part says, which of these pairs are complementary? Well, which one of these can we make up? So we have to first look at the exclusive events. If they're not mutually exclusive, then they're not complementary. They must, first laws, they must be mutually exclusive. So, can A and D, okay, so face cards and aces, do they make up the whole thing? Well, no, they don't. Not all cards are face cards or aces. Let's see this one. Red card and black cards. Hey, yeah, B and C are. All cards are either red or black. Okay, now let's take a look at B and E. B and E. Red card, oh, not B and C, B and E. Whoops. B and E. Now, let's take a look at this one. B and C. Red cards, well, there's still also spades, so that one doesn't count. So it's B and E is the only one that are complementary. Oops, just like that. Okay. All right, here we go. Last page, then we're off to the assignment. So, events have been represented on the Venn diagram. State all the pairs of events that are mutually exclusive. So if we take a look at this, let's first start with A. A and B are mutually exclusive. They are not touching. A is not in B, so A and B. Let's look at another one. What about A and C? Hey, yeah, both of those are mutually exclusive. There's no A in C. There's no overlap in A and C. None of the elements of A are in C. Now let's look at none of the elements of A are in D. Now let's look at B. Well, we already did B and A. Well, Elements of B are in C, so that doesn't count. Elements of B, though, are not in D. Alright, now let's take a look at the next one. And then we just have B and D because C is in D. So that's it. Those are all my mutually exclusive. Here's the next one. Use the given information and the probability formula. Use the given information and the probability formula to determine whether the events A and B are mutually exclusive. Okay, so take a look at this here. We have 1 over 4. So let's look at our formula. Our formula states, well, let's go back, show you the formula here. Here's our formula. So in order for it to be mutually exclusive, this must be true. So let's see if it does. So let's look. P, A or B must equal to PA plus P, probability of B. Probability of A or B must equal the probability of A plus the probability of B in order for it to be mutually exclusive. Let's see if this is true. So we have 7 over 12. Is that equal to 1 over 4, which is the probability of A, plus 1 over 3, which is the probability of B? See if it is. Okay, so I have, well, first of all, not common denominators, let's make them common. Multiply by 3, multiply by 3, it's like cross multiplying. So I'm going to get 3 over 12, and the other one's going to be multiplied by 4, multiplied by 4, common denominator is 12, so that one we have to multiply by 4 plus 4 over 12, and that gives me 7 over 12. So yes, they are mutually exclusive. Next one. A card is drawn from a standard deck of 52 cards. Use formulas to determine the probability that a 9 of diamonds or a heart is drawn. Okay, so a 9 of diamonds or a heart is drawn. So I take a look at this. We have a 9 of diamonds. So what's the probability? A 9 of diamonds or a heart? Well, that is automatically mutually exclusive, isn't it? Like, what is the probability of getting a 9 of diamonds? Well, that's 1 out of 52. What's the probability of getting a heart? Well, the probability of getting a heart is, well, there's 4 suits, so that's 1 in 4. Okay? Now, let's see, PA or PB. PA or B. And there are, well, this one's pretty obvious, there's no one in each one, but I'm just going to show you with the formula one more time. Is equal to, well, let's see, 1 over 52 and plus 1 over 4. I don't know what the probability is, but now we take a look at this here. This is going to be the same thing as 14 over 52. That's just a little practice for you guys. Okay? That's it. So now, next one. A 9 or a heart is drawn. Oh, this is definitely by 4. 9 or a heart. Well, can a 9 be a heart? Yes, so this is not mutually exclusive. It's not mutually exclusive. Okay? Now, let's take a look at this next one. Okay, so we're looking at blocks of different shapes and colors are placed into a bag. There are 3 clubs. There are 3 cubes, 1 blue, 1 red, and 1 green. There are 2 pyramids, 1 red and 1 yellow. There are 5 cylinders, 1 blue, 1 yellow, and 3 red. So, determine the probability that a block of the selected at random will be a pyramid or a club. So, pyramid or a club. Let's take a look here. So, pyramid. Altogether, we have 3, 2, and 5. So that's 5 and 5, that is 10. So altogether is 10. How many are pyramids? Well, a pyramid, there are 2 pyramids. It's 2 and 10. So this probability of a pyramid, I'm just putting a P for pyramid, is equal to 2 out of 10, which is equal to 1 out of 5. Now, what's the probability of a cube? Well, there are 3 cubes. So, P, pyramid, or cube. Now this is definitely mutually exclusive because there are no pyramids that are cubes. We're not looking at colors here. P, pyramid or cube, is equal to 2 out of 10 plus 3 out of 10, which is equal to 5 out of 10, which is equal to 1 over 2. That's it. So, now what is the probability it will not be red? Okay, so how many red ones do we have? We have 3 red, 4 red. So P, not red, P not red is equal to, how many was there? 4. 4 out of 10, which is equal to 2 out of 5. So will be red or a cylinder. So will be red or a cylinder. Let's take a look. There are red cylinders and there's 1 red cube. So P red, oh, will not be red. Sorry, that's 6 out of 10. Sorry, the one before was 6 out of 10. It's late. I'm making mistakes. 3. I counted how many were not red. Just looked at my... Okay. So probability of being red is equal to 4 out of 10, which is 2 out of 5. Now the probability of being a cylinder is 1, 2, there's 5 cylinders. It's equal to 5. Oops. Is equal to 5. I'll make that a bit clearer. Probability of being a cylinder is equal to 5 out of 10, which is equal to 1 out of 2. Now, for this one here, there is an overlap, isn't there? These are not mutually exclusive. We have some red that are cylinders. Okay, so for this one, P, R, or C is equal to, well, we have to add these together. I'm going to keep it out of 10, so it's common denominators. 4 out of 10 plus 5 out of 10. Then we have to subtract the overlap. So now we have to figure out what is the overlap. So how many are in both? I have 3 red in both, don't I? I am using, by the way, this formula right here because we know it is not mutually exclusive because there are some red cylinders. So there are some red that are cylinders. So we have to subtract those away, and that is our 3 out of 10. So that's going to give me a total of, that's 9 out of 10 minus 3 out of 10, 6 out of 10, which gives me 3 out of 5 is my answer. Okay? Last question. Tom and Andrew were asked to solve the following problem. So 200 people with neurology symptoms, which include headaches, backaches, participated in a study to evaluate the pain relief of medicine. All people took the medicine and the results were as follows. 60 people experienced head relief, 126 people experienced back relief, and 36 experienced relief from both. So, this one here is complicated. The easiest way to do this, I would say, is a Venn diagram, like is down in B. So, to solve this problem using a Venn diagram. So, I'm just going to use the Venn diagram right now. I'm going to do part 2 first with the Venn diagram and fill it out. So we have 36 there, right? So how many people out of 36 have both? So how many people would have a headache? I have to subtract 36 from 126, which will give me 90. So I put 90 in there. Now it says 60 people are there, so I subtract 36. It's going to give me 24 for backache, okay? So that's interesting. So there's a subtraction going on to fill out a Venn diagram. Therefore, we know this is not mutually exclusive. So once again, we're going to have to do a subtraction as well. So what's the probability of B for backache? Well, that's going to be 126 out of 200. Okay. So what is the probability of both? Probability of both is going to be Well, 36 out of 200. All right, now let's find the probability using probability formula. Oops, both. Both is probability B and H. Okay? So let's take a look at H. We have probability of B or, that's not or H. Okay? So we have that is equal to the probability of H plus the probability of B minus probability of B and H. Okay, look at that. That's 60 over 200 plus 126 over 200 minus 36 over 200. Well, what does that give me? That's going to give me 186 minus 36 is going to give me 150. And that is the same as 3/4. Well, let's check the bottom here, if that gives us the same answer. This is kind of like what we did in Unit 1. So how many people are there? Out of 200 people, we have 90, 36, and 24. We add those together. So that's going to give me 60 plus 90 is equal to 150. And that is 150 people, and there's a total of 200, which gives me 3 out of 4, which is the exact same answer. There we go. I'll see you tomorrow morning as we work on the assignment together. Thank you very much for watching.